Hello everybody, my name is Walter and in this episode 70 of my Redstone Commands Series. In this episode I want to cover how you can use iteration and recursion to implement more advanced mathematical functions that are not directly available through the sqrt command. Now what is this all about? Well, to put it simple, you can calculate the output value of many functions for a given input value by just going through a series of much simpler calculations over and over until you hit the final result. This is usually done either via recursion or iteration. So let's start with a quick overview of what recursion and iteration are actually about. Beginning with recursion. So for that, we take our problem we want to solve and give it to a program. A type of function, just a series of operations that are done one after the other. Unfortunately, at this point, the problem is just too big to digest. So what happens next is the function or the program calls or creates independent copies, so further instances of itself. They have their own variables, they don't really talk with each other, they are completely independent. And then the problem gets broken down into smaller parts and each part is given to a different function. Then next, the first instance is put into the stack. This is a part of the memory, so they are not running in the processor anymore. This is halted, paused for later. The stack, by the way, is a first in, last out memory. This will become important later on. So now the second generation is working and they do exactly the same. So let's say the problem is still a bit too big. So they call a third generation. Break the problem down and are put onto the memory stack. Now, let's say the problem is simple enough that it can be directly solved. So that is what happens. So the smaller parts are all solved now and the functions stop. Now the previous generation is retrieved from the stack. So this is the first in, last out part. And the smaller solutions are put together to create the next level of solution. And that repeats until we hit the highest level where the whole problem now has been properly solved. Now iteration works a little bit different. Here we start again with the problem and give it to a function. But instead of calling different instances of the same function, we are using a loop to loop through the same set of operations over and over until we have the final result. So how does this work? Well, we need variables that persist between each loop variables, that carry over the required intermediate results, which are then processed over and over until we hit the final values. So how does this work? Well, we have our first iteration and we get closer to the final result, but we're not there yet. So we take what we have and just start once more. So after the second iteration, we are already closer to the final result. And then we repeat this again, get again a bit closer, and then once more until we have hit a stopping condition, at which point we are done and the operation is finished. So instead of breaking down the problem, we are solving the problem partially each time we loop through the operation. So it's similar, but the approach is still different. But what are the main strengths and weaknesses of those two approaches? Well, for one, there are some problems that are better solved with recursion or better solved with iteration. As an example, the binary search I talked about in the episode about lookup tables is a problem that is very easy to solve with recursion, but a bit awkward with iteration. On the other hand, there are also iterative formula, as we will see a bit later in this episode, that are, well, better with iteration than with recursion, or at least a bit more straightforward. Beyond that, recursion, since you have all of those independent instances, allow for great parallelization. And with this, if running on multiple processors, also a great reduction of the runtime. If the programming language you're using actually allows for it, since many of those stem from a time where you only had monocore processors, and back then this wasn't really anything to take into account. The main downside of recursion is that you have all of those instances that are stored, paused inside of this memory stack at some point. And if you have too many of those, which take too much space, memory space, then you can run into a stack overflow, which could cause some issues like the program seizing up, or simply stopping, or maybe overwriting parts of the memory that are used by other programs, which could cause issues. But nowadays with modern computers, this is rarely a problem. Iteration, on the other hand, is much simpler to think through and to implement. But since you have to go loop by loop, you can't really parallelize this. So iteration tends to have longer runtime if you can use multiple processors. One final thing to keep in mind, you can use one to emulate the other in both directions, which is very important since, well, in Minecraft, you don't have actual loops when you're working with commands. So you have to use recursion if you want to emulate iteration. So in summary, recursion means that you have a function which calls itself or another instance of itself to solve a smaller part of the problem with a memory stack in the background. And iteration means that you're repeating the same set of actions using a loop with loop variables, which sadly has to be emulated with recursion in Minecraft. Now, with all of those basic explanations out of the way, let's talk about why you would want to use or not want to use iteration and recursion to implement a mathematical formula. For one, if done right, those tend to be rather efficient, simple, and also fast in comparison to some alternatives. Also, the accuracy is generally very good and can be adjusted. So what often is done is you have, for example, an iterative formula and you check how much has the value changed between two runs, and once you hit a certain threshold or go below the certain threshold, you stop with the runs. That is your stopping condition basically. And that is much more memory space efficient than just using a lookup table with billions of entries and filling up your memory space unnecessarily. So in a sense, this is very efficient also memory-wise. On the other hand, if you're using recursion, you have to take the memory stack into account. But as I said, nowadays, this is usually not an issue. What is also the main downside of this approach, in my opinion, is that there is no universal conversion formula. So there is no mathematical construct. You can just plug in a given formula, and that would give you the iterative formula for that. There are certain types of problems where you have something like that, but you don't have a general conversion formula. So if you are looking for a specific function, you would have to check if there is actually something like that available. And with that, I think it's high time to show an actual example of an iterative formula. For this, I decided to go with the square root of x, which can be done via the Newton-Raphson method, which gives you in this formula here. Basically, when x is a negative number, there is no valid output, since this is only meant to give you real numbers, not imaginary numbers. If x is 0, then the result is 0, and if x is a positive number, then you use this iterative formula here, which basically can be read as the new y value is the old y value plus x divided by the old y value and the whole thing divided by 2. And for the next loop, the new value becomes the new old value and then so on and so on. If you do this often enough, then this will converge on square root of x. Now, obviously, you need some kind of starting value for y, and this is pretty much up to you what you choose, but a common starting value is just x half. You can also use x or, for example, just 1. It's up to you, but x half is commonly used. But what does this actually mean, or how does this look when we put this into a graph? Well, let's say this here is the square root of x. So this is the target graph, basically. Now, our starting values would be x half, which is this linear graph here. And now after one iteration, we get this graph here, which is already much closer than just the linear graph before. Although you can see small values, we have a difference, and big values, we also have still a difference. But that changes quite enormously already with the second iteration. You can see big numbers are pretty close. We are also getting closer in the smaller numbers, although around 0, we are still way off. So let's iterate once more, and we're getting better and better and better until we hit a point where there is no real difference anymore. So as you can see, this is a very efficient algorithm that within just a few iterations gets you to a very, very accurate result. And usually what you want to do is just determine how much has y changed between two loop runs. And if you go below a certain threshold, then you simply stop with the loops and continue with your normal program. Now following that, let's have a quick look on how you could implement this specific example using Minecraft commands. For this, I've prepared two functions. The first is initial setup and starting values and so on. And the second is where the actual looping or recursion happens. So I've set this up as a function with macros. So during the first function call, I'm actually giving it the x value and the target accuracy. By the way, if you haven't watched my episode about how you can emulate fixed point operations, you should do this before following here, since otherwise you would get a bit confused potentially. Nevertheless, I'm using the formula from before, so y equals y plus x divided by y divided by 2. And the starting value y is x half. Now with the scaling factors involved, I have to add the scaling factor 1000 I've used here additionally to my division in the middle there. And well, that's all I need to be aware of here. So first things first, I prepare the objective, I'm setting the display, and then I'm setting my starting value, temp_x, which is given via the macro call. Then I check if I'm either in the negative, then I just return a fail, or if I'm at 0, then I return 0 and I set the temp result also to 0. Then I set my start value for y, so I need the value 2, so I can divide by that, and then I set my temp value in there, and then I divide by 2. That's all I have. So temp y is my starting value at this point. Then I start with my iteration, and once that is done, I return the temp result and stop with the calculations here. And at a later point, I could potentially get rid of the values or the no longer needed objectives, but that is something that depends on what you actually want to achieve with all of this here. Now, let's have a quick look at the actual iteration function here. So, as I said, the formula is basically the same as before, just with the scaling factor. And this here is a straightforward implementation of that. So I have my scaling factor, then I have my x value multiplied on top, then division by y, then addition of y, and then division by 2. So straightforward, just a formula. Now it gets a bit more interesting. I compare the previous y value with the new y value. And if that is above my accuracy, so the number is higher than the accuracy I want, then I run the loop once more. And this last part here is just a little message, so I can actually see in the dialog how many iterations I've run this. This is completely optional, it's not really needed, but I think it's interesting to see how many operations it actually needs until you hit the target accuracy. And that brings us to the last part for today, which is showing you this in action. So for this, I've used the implementation I just showed you. And the values I choose for x are -1, 0, 2, 3, and 16, properly scaled up, obviously. So in the actual function call, you would have -1000. The accuracy for all of those here is set to 1, which equals 1 promille. And yeah, let's just go through this. So -1, this is the first special condition we're checking for. And you can see we have a temp_x, but we don't have a temp result. And the returns 0 you can see in the chat window is actually a failed 0, not a valid 0, 1. 0 as a number. This changes when we have our square root 0. At that point, we also have a temp result 0, and the return 0 is now a successful 0. Plays a role if you're using this, for example, in the execute command function call. But we still didn't have any iterations since those were just the premature checks. Then, once we have, for example, a 2, we get the 1.414 as a result, as we would expect, and we have 4 iterations. And also, as you can see on the right side here, the last 2 runs were actually the same number as a result. So the temp diff, the last one, was 0. So we are very likely at the correct value there. For 3, we have just 3 iterations. The value is 1.732 as expected, and also the temp diff, the last one, was also 0. And then final example is the 16. 4 iterations, result 4 as expected. And the last temp diff is 1. So the last 2 runs actually had slightly different values, but we are within our accuracy. On a last note, I would recommend to avoid accuracy 0. There can always be the worst case happening that you are, for example, oscillating around a certain number, or maybe some other rounding errors occur, and you never hit 0 as an accuracy. So always try to give it a little bit of wiggle room just to be on the safe side. And with that, we've reached the end of this episode about iteration and recursion. I hope you enjoyed it. I wish you a nice day, and well, see ya.